So hello everybody, and welcome to this acoustic webinar, which is the first one that opens our acoustic webinar series into 2014. Today's topic is solving higher frequency acoustic radiation problems with improved efficiency. So if you have attended 1 year ago, also more or less at the same time, the acoustic webinar, we were talking about acoustic radiation analysis. So today, the topics will be a review of acoustic radiation and introduction to several techniques that allow us to improve the efficiency as well as going to higher frequencies and dealing with larger problems. So the agenda of today is first a short introduction to the Actran software suite. And then we continue with acoustic radiation analysis. First, again, a short review of simulation process using the traditional infinite element method with two small sample applications followed. And then I will present three techniques, relatively new in Actran since several months. The first one is the adaptive perfectly matched layer, or APML. Second one, integration mapping technique, allowing mapping efficiently the structure results onto the acoustic mesh. The third one is to use Actran DGM, or discontinuous Galerkin method, for acoustic radiation analysis. Now I'll perform a very small demo in Actran before the final Q&A session. First, an overview of Actran software suite. Well, Actran is generally a finite element-based acoustic simulation software. As we can see, it is divided in several modules to tackle different acoustic problems. The basic module is Actran Acoustics. It allows performing acoustic radiation analysis from vibrating structure, which is exactly the topic of today. It also allows performing acoustic propagation in duct systems. Now, when we combine the acoustic feature with other physics, then we will develop in different tracks of the Actran software module. On the left, we have the vibro-acoustic track. The vibro-acoustic module allows strong coupling between acoustic field, either internal or external acoustic field, with flexible modeling of the structure. As we can see here, a loudspeaker model involving the flexible structure and the internal cavity, as well as the external acoustic radiation field. As we go further, we have the module called Actran for Nastran. It is a method that combines the strengths of both Actran and Nastran. So the strength in Actran being the accurate modeling of porous material, the strength in Nastran being capability of large-scale model analysis. And when we combine these two, we will be able to solve large vibroacoustic problems involving porous material. So typical application will be the NVH problem of trimmed vehicle body. Then when we combine the acoustic feature with CFD, or turbulent analysis, then we will have the Actran aero-acoustics module, where we can import unsteady CFD results performed by several commercial CFD code in the market, and extract acoustic sources in Actran and perform acoustic radiation analysis. Now on the right, we have two special modules that were initially designed for the aircraft engine acoustic problems. Actran TM, TM stands for turbo machinery, and Actran DGM, which is the most particular module, and DGM stands for discontinuous Galerkin method. It was initially designed for the aircraft engine exhaust noise problem. And as we will see today, we can also use Actran DGM to perform acoustic radiation from vibrating structure. So the main topics will be acoustic radiation analysis. It studies the sound radiation due to any vibrating structure. And in such analysis, Actran can help you to achieve several types of goals. First, predicting. We want to get accurate results. For example, we want to calculate accurately the sound pressure level at different virtual microphones surrounding any vibrating structure, for example, a engine or powertrain component. We want to calculate the radiated power from that structure. So that is called predicting. And moreover, we would like to understand better the physics behind that. And this is the strength of simulation software that get you understand the physics. For example, we want to calculate not only results on several points, but also get a whole picture of the acoustic directivity or color map surrounding the structure. We want to get not only one single value, but also panel contributions, elements contributions from the structure to the acoustic radiation result. And also bear in mind, we have the notion of structure radiating efficiency, which means the most vibrating part, the part that vibrating the most significantly, not necessarily the part that are emitting acoustic energy the most significantly. So with Actran, we can also study the radiating efficiency of any structure. And finally, about improving the design, so Actran is also featured with extensive capabilities to help you to improve the design. For example, adding insulation cover as the obstacle of the acoustic radiation, or absorbing material like foams in the cover design. So a review of the simulation process of acoustic radiation from vibrating structure in Actran. We are using a decoupled method for acoustic radiation in air. Well, when we have acoustic radiation in water, then we cannot use that decoupled method. But as we have the media being air, then this method is acceptable. So in the first step, we will perform a structure analysis using a typical SEA tool like MSC in Actran, but also tools like ADAMS involving flexible body or MARC for some nonlinear issues, or even Actran. As you know that in Actran, we also have a structure solver. So here, typically, we are studying the vibration of the gearbox. And this analysis can be either in frequency domain or time domain. And we will get the surface vibration from that structure using the first step tool. And then the frequency or time domain solver in Actran will handle the acoustic propagation into free field. The typical post-processing outputs in Actran are colored maps, frequency response functions, if the analysis is frequency domain, waterfall diagram for multi-load case or multi-engine RPM problems, panel contribution or elements contribution. Well, we see here the color on this gearbox surface indicating the contribution of that element to a measured or a simulated acoustic result in far field. Acoustic directivity surrounding a gearbox. Animation. Well, when the simulation is in time domain, we will also get time domain pressure results. and subsequently we can produce a sound file. I will play a sound file in another example later on. Now, in this typical modeling process, let's take a look at the acoustic mesh that is required. So first, let's suppose that the vibration is already calculated using a first step in a dedicated tool, and then in the second step, we will need 3 parts in an acoustic mesh. The first one is an interior surface. So this surface is a tight wrap surface surrounding the vibrating structure. And the purpose is to map the structure vibration to the acoustic mesh. In Actran terminology, we call this surface a boundary condition mesh surface, or simply a BC mesh surface. And then using the traditional infinite element method in Actran, we will create an external surface, which is a convex shape that is used as the infinite element surface. So the purpose of infinite element is to let acoustic wave go through that surface without any reflection. The second purpose of infinite element is to predict accurately results in far field where acoustic mesh is not existing. And between the infinite surface and the BC mesh surface, we will fill the volume with acoustic volume element. Let me give you 2 sample applications. Both are real industrial applications using Actran. I would rather say using Actran simulation chain with a structure code. The first one is a powertrain radiation problem. It's a truck powertrain, relatively large. You can see the size on the screen. So to solve the powertrain radiation problem, we use 3 different software to form a simulation chain. The first one is the multi-body dynamics software that calculates the realistic mechanical loading on the structure. And in the second step, a FEA software will calculate the surface vibration on the powertrain. And in the third step, the acoustic radiation analysis is done in Actran. The measurement is performed in an anechoic room at different RPMs. Here we are comparing the Actran result and the experimental result at that RPM. And the curve shows averaged acoustic result at different several microphones surrounding the powertrain, and we see extremely matched, a very good, extremely good matching between these 2 results. And further than that, Actran can also help you to get an idea of the contribution of different panels on the powertrain to the acoustic power radiated by the structure. So here we are seeing that the structure is divided into different parts. And we see that the blue part, although it's quite small, it is vibrating quite significantly and consequently radiating quite significantly. The reason behind that is that we have a different material which is lighter on the blue surface than on the rest of the powertrain system. And the second example is the simulation chain between Adams and Actran to solve a piston slap noise. So here the uniqueness of this project is that we do not involve a dedicated structure FEA tool. We are solving the FEA part in Adams, or more concretely, the Adams flexible body capability. So in this piston system, the internal components are modeled as rigid bodies, while the cylinder block is modeled as flexible body in atoms, and the input is the increasing speed of it's a speed up of the crankshaft rotation speed, and atoms output acceleration on the surface node of that block. And a time domain solver in Actran solves the acoustic radiation. So here we are seeing the animation of atoms. And on the left, we see the acoustic model in Actran. It's basically a infinite element model with the piston cylinder block enclosed by the infinite element surface. I'm going to also play the sound produced by the Actran analysis, and I hope you can hear that clearly, the run-up of that system. Very nice and realistic sound produced by Actran. Okay, so that was a review of the infinite element method for the acoustic radiation. Now I will introduce the PML method and the APML method. So PML is also called perfectly matched layer method. It is basically an alternative or a complement method to the existing infinite element method for acoustic radiation. And in the PML model, we still have here in the green area and vibrating structure, or simply some analytical acoustic sources, can be simple sources, or even aero-acoustic sources by Actran aero-acoustics. And we will have a acoustic component for the near field acoustic propagation. And then we are adding an extra layer, that is the PML layer, that amps progressively the acoustic wave through its thickness. And far field result is solved using a Fox-Williams-Hawkins solver, or FWH solver, in the PML model. There are some benefits of the PML method compared to the infinite element method. First, as we know in finite element analysis, there is a impedance matrix related to the finite element system, and when we have infinite element method, the impedance matrix is a unsymmetric one, and with perfect matched layer method, that matrix is a symmetric one, and this consequently will lower the number of degree freedoms, especially for higher frequency problems. Benefit is to allow us to have lower CPU requirement for the same type of problems. And like infinite element method, with PML, we can also analyze acoustic radiation in a semi-free field. So this allows to simulate a acoustic test, for example, in a semi-anechoic room. Now, so after PML, the next concept is the APML, or adaptive PML. Now the issue arises from actually two opposite constraints related to the PML method. As we do acoustic analysis, we have the notion of acoustic wavelength. So let's take a look at this red area, which is the PML region. So at lower frequencies, the acoustic wavelengths are generally longer, and to absorb efficiently that long wavelengths through the PML, then we will have thick and large PML regions. While at higher frequencies, the acoustic wavelengths will be shorter, and as we are using a discretization-based method, the individual element in the PML region will be small. So as we are analyzing problems through a large frequency range, one single PML mesh is not the optimum solution. And for that reason, we implemented the APML, which automatically generates the PML mesh according to different frequencies. So at lower frequencies, the PML region is larger, containing also coarser elements inside. And at higher frequencies, Actran will reduce automatically the PML region and generates smaller elements in that region. So each frequency can be optimized by the APML automatic meshing. And in practice, when we analyze a large frequency range using APML, different sub-frequency ranges will be created, and the keyword adaptive factor will drive the creation of those frequency ranges. So the factor 2 means that the ratio between the higher bound and the lower bound of any frequency range will be 2. So this factor can be selected automatically by Actran or the user, and also manually input that adaptive factor. So as the mesh is adapted for different range of frequencies, a gain of computation time can be achieved using APML. Now, the second technique I would like to introduce to increase the efficiency of acoustic radiation analysis is the integration mapping method in DC mesh. So we're talking about mapping the structure result onto the acoustic mesh. We have two different methods, either on the left, a standard sampling method, or on the right, a integration mapping method. We are going to compare the different mechanisms of these two methods and highlight the benefit of the integration mapping method that is available now in Actran. So with standard sampling method, we are first having the structure mesh, which is relatively fine, refined mesh. And in acoustic analysis, in vibro-acoustic analysis, usually the acoustic mesh is coarser than the structure mesh because we are having different criterions for the matching the acoustic domain and the structure domain. So when we use standard sampling method, the acoustic nodes are located in different structure meshes, but you can see not all the structure mesh will receive will have some acoustic node inside it, and consequently some possible information loss is expected in the sampling approach. Now, with the integration method, we are doing the mapping the other way around. We take the acoustic nodes or acoustic elements that are generally coarse, and we look for structure nodes that fall into these acoustic elements, and then use the shape functions of these acoustic elements to distribute the information or the energy received from the structure vibration to the acoustic nodes. And with this method, all the structure vibration information is conserved in that mapping process. So the benefit is clearly as we will be able to match the acoustic domain in a more cost way, the computation time can be reduced, and higher frequency would be reached. So a simple example that compares the two different mapping methods. We have a vibrating gearbox at a certain frequency, and we are using two different acoustic meshes. So here we are showing the internal wrap mesh for the acoustic domain. So it is really the closest acoustic surface to the structure, and one has the same level of refining as the structure mesh, and the other one is rather much more coarse and follows only the acoustic meshing criterion. Now, when we use the standard sampling method with the significant divergence between using these two mesh, we are looking at the directivity surrounding that gearbox at 1535 Hertz. And now when we use the integration method, which is an option today in Actran, we obtain the same result using these two different meshes. Okay, so that was the integration method. And the last point of today is the acoustic radiation using the Actran DGM technology. So as I explained at the very beginning of this webinar, Actran DGM is a very specific module in the Actran software suite. It is a different type of finite element method, and it's still a discretization-based method. So we have volume meshes, and the implementation in Actran is that it's a time domain solver, and with result also available in both time domain and frequency domain for the post-processing, and it solves a linearized Euler equation, or LEE, which is different from the Helmholtz equation that the let's say the classical Actran solver solves. And as it's a time domain solver, the Actran code can select the sorry, I didn't mention the element order. So each element has a different order ranging from 1 or 16, and the code is able to select the optimum element order and time step. And initially, Actran DGM was developed for the aircraft engine acoustic propagation. So acoustic propagation in a very non-uniform and rotational flow, as its case as exhaust of the aircraft engine. And its attributes is to be able to deal with very large model. So typically today we can solve a DGM model including 500 cubic meter of air with complex convection condition, and simulating that program at up to 1200 Hertz. And second attribute of DGM is that it's very highly scalable. So typically we can run a DGM model, a huge one, on hundreds or even thousands of CPUs, with each CPU requiring only very low memory consumption. Now, since Actran 14, Actran DGM has a new implementation in Actran. So we implemented the BC mesh method also in Actran DGM. So today, apart from solving aircraft engine acoustics in DGM, we can also solve problems like acoustic radiation from a vibrating structure. So same problem as we presented just now. And so the power now of DGM in such a problem is to allow us to solve normal size problems, for example, gearbox or engine acoustics at very high frequencies, thanks to its power. And another possibility is to solve acoustic propagation or simply acoustic propagation and scattering problems at higher frequencies. For example, if we want to solve the acoustic propagation from around a vehicle to solve the pass-by noise, then we can also use DGM to arrive at larger problem scale and higher frequencies. So just give you an idea of what we can arrive today. So as in the last cases, we are not having a significant convection, so we're not having a flow effect. For example, in automotive industry, the Mach number is far lower than the in aerospace industry. So the acoustic waves are less compressed than in the case of aircraft engine, and we can still have even larger DGM elements and even push further the frequency up to far higher than 1,200 hertz, as is the case in the aerospace industry. So in practice, Actran DGM is able to use a vibration boundary condition or BC mesh, either in time domain or frequency domain, calculated by, for example, Actran. So in the first step, if we go to time domain, then the Actran solver 112 will solve the gearbox vibration and produce transient citation on that surface. Or if we want to perform frequency domain analysis, then the Actran solver 111 can be used to get harmonic frequency domain excitations for the dynamic analysis. And a Actran DGM mesh also involves different regions, as we can see. So at the very center, we have the coupling surface. That is the wrap of the structure surface. And then we will have a physical component for the acoustic wave propagation. On top of that, buffer zone for the wave damping. The purpose of this buffer zone is similar to the PML as we have seen previously, but the technology in DGM is slightly different from the PML method. And we are able to solve far-field radiation problem using a SWH method. Now with that, I would like to conclude today's presentation. So Actran is well suited to perform acoustic radiation analysis by either using Actran technology or by a simulation chain with MSc Actran or Adams or other FEA tools available in the market. And Actran has frequency domain and time domain simulation capabilities with rich post-processing possibilities. And for acoustic radiation problem, different improvements have been made recently in Actran. The first point, the implementation of APML will help us to solve acoustic model with increased efficiency. The integration mapping method allows a coarsened acoustic mesh and allows us to gain computational time. And the BC mesh feature in Actran DGM allows to compute the acoustic radiation from vibrating structure at much higher frequencies using a time domain approach. So with that, I will close the presentation and show you very quickly the interface of Actran. So now we are looking at the Actran VI, which is Actran Graphical User Interface. And the model that I created is a gearbox radiation model. As we see, the acoustic part has several regions. First, the acoustic volume mesh, and the interior surface that we call a coupling surface, which is the wrap of the internal structure. And the APML surface is just the exterior surface of that of the whole model. And as we look at the APML component, we see there are actually several options that are left blank. So if the user desires to, he or she can indicate some parameters to drive the generation of APML meshes. Otherwise, these options can be left blank, so Actran will create the different APML meshes according to different frequencies being analyzed. And in the DC mesh component, we are projecting a structure result into the Actran interior surface. As we can see here, we can select the mapping method, either using a standard sampling method or use the integration method. Okay, I will not launch the computation now. I did that before the webinar, and I will simply show you the result being calculated. But the result is the sound pressure value at different microphone positions surrounding the gearbox. You can also plot the directivity at different frequencies. For example, we can look at the certain frequency, for example, 450 Hertz, and plot a directivity around at that frequency. So with that, I will close the